Welcome back to Anton Math. Now we just finished choosing marble problems, and in this video we're going to do a type of problem that's probably one of my favorite problems. I do enjoy playing poker. It's a small passion of mine, so figuring out the probabilities of different poker hands can be kind of fun, and all those other poker aficionados out there are probably going to like this video. So let's do an example, and I've just made this a pretty big example, so we'll just do this one for this video. But a poker hand of 5 cards is dealt from a standard deck. So for you poker people out there, we're playing 5-card stud. But what are the probabilities of the following hands? So the 4 kings and the ace of spades, a full house, and a hand with no pair. So first of all, for all of these different problems, we're going to have a sample space S, where S is all possible 5-card hands. Now we have 52 cards in a standard deck, so all possible 5-card hands has the, there are 52 choose 5 possible 5-card hands, I should say. And this number, just for reference, this is equal to 2,598,960. So when you're playing poker, there are a little bit over 2.5 million possible different 5-card hands. Now, of course, the differences might be small, right? I could, a difference between two hands might just be that one of the cards is of a different suit, right? But this incorporates all of those different possible hands. All right, so let's take a look at number 1. First, for number 1, this is the 4 kings and the ace of spades. Now, this is an easy one, because we want to look at how many possible hands fall under this category. Now there's only 4 kings, so there's only one way to choose all the 4 kings. There's only one ace of spades, so there's only one way to have all 4 kings and the ace of spades. So for 1, the probability is just 1 over this number, about 2.5 million. The probability that you will get this exact hand, because this is only one hand, I guess is what I should say. This is only one hand out of all of my possible 2.5 million hands. This is one of them. So the probability of getting this one hand is 1 over this large number. All right, so pretty easy one there. Let's look at number 2. Number 2 is a little bit more complicated. Number 2, I'm looking at the probability of getting a full house. Now, for those of you not familiar with poker, a full house is when you have 3 of one denomination and 2 of another denomination. So for example, 7, 7, 7, 5, 5. This would be a full house, 7s over 5s. So there's a couple different things we need to look at, and we're going to start with the triple first. So I need to count all of the different denominations I could have for my triple, and then I need to count for each of those denominations how many arrangements of suits I have, right? There's 4 suits for every denomination. And then for each of those arrangements of my triple, I need to look at the possible denominations of my double, and then look at the possible suit arrangements of my double. And using the multiplication principle, the product of all of those things is going to be the order of my event space. So first we're going to calculate the number of full houses. In other words, the order of E. This is the total number of possible full houses. So looking at the denomination of my triples, there are 13 possible denominations. And so there are 13 choose 1 ways to choose the denomination for my triple. Now for each of these denominations that I choose, I can arrange my suits. I have 4 different suits, and I need to choose 3 of those suits for each denomination. So let's say my denomination is 7. There are 4 choose 3 ways for me to have 3 7s if I look at all the different combinations of the suits: hearts, diamonds, spades, and clubs. So there are 13 choose 1 times 14 choose 3 ways to get 3 of any denomination, to get a triple of any denomination, right? 4 choose 3 ways to get a triple of a particular denomination. And so based on this, now I need to look at my double. Now, after I choose my denomination for my triple, I have one less choice for the denomination of my double. So there's 12 choose 1 ways for me to choose the denomination of my double. There's only 4 of any card, so I can't have 3 7s and 2 7s, for example. So for whatever I chose over here, I can't choose that here again. And for each possible denomination choice for my double, there's going to be 4 choose 2 ways to arrange my suits for those 2 cards, right? So 13 choose 1 is just 13. 12 choose 1 is just 12. 4 choose 3 is 4, and 4 choose 2 is 6. So I'm not going to do this out, but let's just leave it as 13 times 12 times 24, let's say. So this is my event space. So then the probability of my event, since we're in a uniform environment, all possible 5-card hands have the same probability individually of what we found in part 1. So this is going to be the order of E over the order of S. Or in other words, 13 times 12 times 24 over this number up here, 52 choose 5. And you can do this calculation on your own, make sure you get the same thing. But when I did this out, I got 6 over 4,165. So the probability of getting a full house in 5-card stud is 6 in 4,165. It's a little bit more than 1 in 1,000. All right, it's about 1.5 in 1,000. So not very good odds of getting it in 5-card stud. All right, now we have this last problem, a hand with no pair. A hand with no pair. Now we're going to do this similar to how I did the last problem. I want to look at the order of my event space, E. Now if I have no pair, that means that all of my cards have a different denomination, right? A pair just means that I have 2 cards with the same denomination, like I have 2 5s or something like that. So no pair means that I have all different denominations. Now how many ways are there to choose 5 cards with different denominations? Well, there's 13 denominations, and I want to choose 5 different denominations. So there are 13 choose 5 ways for me to arrange my denominations without having any pairs. Now we still need to look at the total number of hands, not just the total number of ways of denominations. So for each of these cards, let's just say I have, ace, 2, 3, 4, 5. Let's say I had a straight. I still have no pair, so this is a possible hand with having no pair. Now for the ace alone, I have 4 different ways to choose my suit, right? I could have a heart, a club, a diamond, or a spade. For the 2, I have 4 different ways to choose my suit. For the 3, I have 4 different ways to choose my suit. For the 4, I have 4 different ways to choose my suit. For the 5, I have 4 different ways to choose my suit, right? So for every selection of 5 different denominations, I have 4 to the 5 ways of arranging the suits of those denominations. All right, now this is a little bit tricky, so if you don't get this, make sure to think about it a little bit. I have 13 choose 5 ways to choose my 5 denominations in a hand with no pair. And for each of those choices of 5 denominations, I have 4 to the 5 ways of rearranging their suits, or of exchanging out cards for the same denomination but with a different suit. So the probability of having no pair is going to be 13 choose 5 times 4 to the 5th all over 52 choose 5. And when I simplified this down, I found this to be 2,112 over 4,165. So a little bit more than half of the time, if you deal 5 cards, there will be no pairs. And a little bit less than half of the time, there will be at least 1 pair. Right? This doesn't mean that 1 minus this would be how many have a pair, but it means how many have a pair or a triple or multiple pairs or 4 of 1 card or a full house or all these different things. It just means that there's at least 1 pair. Right? All right, now that's the end of our card problem. I hope you had fun with this one. In the next video, we're going to talk about choosing a committee. And we did lots of choosing a committee problems before when we were counting. So we're just going to be applying the same counting principles we did before, but now finding the probability like we have in these videos. We'll see you there.